Good afternoon, everyone. Today we're going to solve an equation, namely x is equal to the square root of 2x squared minus 8 plus 2. And we're going to do so both graphically first and then to check our solutions algebraically. Now, graphically means that we have to graph both sides of this equation independently on the same graph, on the same set of axes, and find their points of intersection. Now, since we're solving by algebraically afterwards, we're not going to start messing around with the equation manipulating it algebraically before we start graphing it. That would kind of defeat the purpose, right? And so whenever we're tasked with solving some equation graphically, we have to graph both sides of the equation as they are, okay? So if we want to do that, starting by graphing the left-hand side, that's just the line y is equal to x. Now, you have to be somewhat precise when we're trying to solve things graphically, right? Because the points of intersection are somewhat sensitive to the precision of our graphing. Let's try to do a decent job. So I'm going to try to put some points to anchor myself here. Y is equal to x is when the x and y coordinates are the same. And so I'm going to plot a few points and hope that that gives me enough structure to draw a decent line, something like that. And let's do the same in quadrant 3. And let's say, already getting a little bit funky. Let's hope this is enough, okay? So again, graphing the left-hand side by itself, this is the line y is equal to x. Now, the right-hand side is where we're really gonna have to put some effort in, right? And so how are we gonna go about graphing the square root of 2x squared minus 8, the square root of a parabola, and then shifting it up by 2 plus 2 at the end? Well, first thing we can do is look at the expression inside of the square root. Let's take a moment and do that. If we look at just 2x squared minus 8, what do we know about this function? Well, we know that it's a parabola with an a value of 2, and this is in vertex form, if you can recognize it. And so this y-intercept doubles as a vertex, and we know its coordinates are at 0, -8. And so we can start plotting that. I'm going to plot it as a dashed parabola because we know it's not the actual end product of this right-hand side, but it's part of the process. And so I'll draw first the vertex at -8. And now we can, what we can do with this function is write it in factored form to get our roots, right? Our x-intercepts. So we can factor this as 2 times x squared minus 4. And finally, we can recognize this to be a difference of squares and factor it completely as 2x minus 2x plus 2, meaning that we have our roots at 2, 0 and at -2, 0. So those points will turn out to be helpful. We have our vertex at 0, -8, 0, -8, pardon me, at 2, 0 and -2, 0 for our roots. And then from that point on, we have an a value of 2. And so applying the pattern that you know about quadratic functions, we know that from the vertex, we go over 1, up 1. Now, this is like a vertical stretch of 2, so we'll go over 1, up 2, rather, and end up here, and symmetrically here as well. And then over 2, up 4 times 2 means up 8. That's why we get to the roots at 2. And so we know that our parabola is going to look something like this. It's starting to take shape. If we want to go a bit higher, right, the pattern would be over 3, up 9, now up 9 times 2, i.e. up 18, right? And so over by 3 horizontally, up 18 vertically takes us to the point 3 and 10. 1, 2, 3, 4, 5, 6, 7, 8. Somewhere around here. Let's say this won't be too important for our solution, but trying to keep some level of precision. And symmetrically, we also get a point at -3 and 10, somewhere in this region. And so again, as a dashed parabola, here we go. This is again just the stuff underneath the square root 2x squared minus 8. Now, knowing what you know about taking the square root of entire functions, we can now graph the square root of this green parabola. Let's go ahead and do that. So we know that we can only take the square root of non-negative values. So between the two roots, we will have nothing. Our function will be undefined, right? Because the y values of the parabola are negative between the two roots. Now, at the two roots, we're going to get 2 invariant points because if we're taking the square root of the y-coordinates being 0, the square root of 0 is 0 itself, and so we get invariant points at 0. We also get them at y is equal to 1, because similarly, the square root of 1 is 1. Okay? Now, from that point on, we don't have that much information other than as the x's get bigger and bigger, the square root of 2x squared minus 8 is going to behave like the square root of 2x squared. What I mean by that is as the x gets sufficiently big, the minus 8 doesn't have much of an impact on things. And so this starts to look like approximately this. And the reason I mention that is because we can simplify this. This can be written as the square root of 2 times the square root of x squared, okay? And that can be written as the square root of 2 times the square root of x squared is the absolute value of x, okay? And now we're going to draw these curves in both directions. And you know the absolute value of x graphs look like a V shape. They're symmetrical, right? And so they're a line in either direction. And so the absolute value of 2, that's approximately 1.4 times the absolute value of x. The reason I approximated the root 2 to be 1.4 as a numerical value is just to highlight the fact that 1.4 is bigger than 1, which is the slope of this y is equal to x line, the left-hand side of things. And so this is going to be a steeper line, okay? I mentioned that because that means that we're going to hook like so, and then this should be a bit steeper. I didn't do a great job there. This should look steeper than the line. And so it should be something like this. And I won't make it cross because that's going to be messy, but I'm also going to make it a dashed line because this is still not the end product, right? Just the square root of 2x squared minus 8 is not the end goal. We still have to shift it up by 2. You can imagine this plus 2 at the end as a vertical translation of 2 units, okay? So this is still just part of the process. And the same thing on the left-hand side. You're going to hook between 0 and 1 because between 0 and 1, the absolute value of a number is bigger than the number itself. So we get a nice little hook here, and then this goes up pretty steeply. That's somewhat precise, okay? Now, the final step to fully graph our right-hand side is to shift the square root function up by 2 units. And so let's grab both sides of this dashed blue curve and shift it up by 2 vertically. So what that means is that this invariant point at 2, 0, one of our roots, is shifted up by 2. That means it's going to 2, 2. 2, 2 is a point on the line y is equal to x, because at 2, 2, y is equal to x, meaning it has to be on that diagonal line. That's important because this is a point of intersection. This is going to be our very first point of intersection. The next invariant point at y is equal to 1 and somewhere a tiny bit to the right of x is 2, that'll go up to from y is 1 to y is 3, and so that'll be somewhere around here, okay? And then again, I mentioned the fact that this eventually behaves like 1.4 times the absolute value of x, meaning that it's going to be steeper than the line with slope 1, right? Slope of 1.4 is greater than 1, and so this will never intersect that line again, and it'll trail off like so towards infinity, okay? And symmetrically on the other side, the root at negative 2, 0 is going to go to negative 2 and 2. This invariant point at y is equal to 1 is going to go to y is equal to 3, and a bit to the left of our point at negative 2 and 2. And then symmetrically, we're going to get this little hook, and then this shooting off to positive infinity. That is the full graphing of this right-hand side of our equation. And so this curve, this black curve, is roughly the curve, the square root of 2x squared minus 8 plus 2. That, I would say, is the most effort requiring part of the solution. Now, reminding ourselves what we're here to do is to solve this equation graphically. That means looking for the points of intersection between these two curves, this one and this one, And since this equation is only in the variable x, makes no mention of y, our solution should reflect that, and our solution should be simply x is equal to whatever the values might be, whatever the x coordinates of our points of intersections might be. And so you see this point of intersection is at 2, 2. That has an x value of 2. So our solution is x is equal to 2. And that's the only point of intersection. I don't see any other even close candidate for a point of intersection. And I did check in with graphing software earlier. This is reasonably accurate for a depiction of our graph. And so that is going to be our one and only point of intersection, meaning that x is equal to 2 should be our one and only solution. Now, we're going to solve this algebraically so we can check our work, and then we'll verify those solutions by plugging them back into the original equation, and we'll see if there's any extraneous solutions. My guess is that there will be. So let's go ahead and do that. Let's carve out a piece of this whiteboard to solve algebraically. So solving this using algebra, we'll have x is equal to the square root of 2x squared minus 8 plus 2, right? This is a good old-fashioned radical equation, so we should probably isolate the radical on one side to make our lives as easy as can be. We'll do that by subtracting 2 on both sides. And now we have x minus 2 is equal to, again, the square root of 2x squared minus 8, like so. Now we've successfully isolated that radical. There's nothing left to do but square both sides, right? Let's be mindful of what we're doing on the left-hand side. We are squaring all of x minus 2, right? We're not squaring each term individually, as might be tempting to do, but we're squaring a binomial. And so this expands out to be x squared minus 4x plus 4. And conveniently on the right side, we get the square root and the square canceling out. And so we get 2x squared minus 8, like so. Now, this is a good old-fashioned quadratic equation. Let's move everything on one side. Feel free to do this on your own. Pause the video if you'd like. Move everything on one side. The greater quantity of x squared is on the right-hand side. I want to keep my x squares positive, so I'm going to move everything onto the left side. And so you guys know how to do that. Subtract x squared on both sides. Add 4x on both sides and subtract 4 on both sides. And so now, like we wanted, the left-hand side is 0. And we have that equal to 1x squared plus 4x minus 8 minus 4 minus 12. And that is a pretty nice quadratic equation to solve. We can factor this. This factors readily as x plus 6 times x minus 2, meaning that we get potential solutions, right? Because we have to verify them to see if they really work, given the properties of radical functions and potential restrictions. And so we get potential solutions. Again, x is negative 6 or x is positive 2. Now, x is positive 2 was the one unique solution we found when solving graphically. So that should probably be a sign that this will work out. X being negative 6 is nowhere to be found. Let's see what happens when we verify our potential solutions by plugging them back into the original equation. So I'll bring you over here to verify our solutions. If x is equal to 2, we're plugging x back into the very original equation before any manipulations were done to it. And so we're looking to see if 2 is equal to the square root of 2 times 2 squared minus 8 plus 2. There are a lot of 2's. So is 2 equal to the square root of 2 times 2 squared is 2 times 4, which is 8 minus 8 plus 2. 2 is equal to the square root of 0 plus 2. And certainly 2 is equal to 2. And so x equal to 2 is a good solution. And so this is a good solution. Let's try to see if x being negative 6 results in the same thing. I'll plug it in here to not go off screen. If x is now the value of negative 6, let's plug it back in again to the original equation always. And so we're looking to see if negative 6 is the square root of 2 times negative 6 squared minus 8 plus 2. Negative 6 is equal to the square root of Negative 6 squared is 36, times 2 is 72. And now your skepticism might be growing that this does work. Negative 6 is the square root of 64 plus 2. And so that says that negative 6 is equal to 8 plus 2, which means negative 6 is equal to 10. And that is certainly not the case, right? If the square root of 64 was taken to be negative 8, that would work. But given how radicals function, that is not the case. And this tells us that x being negative 6 is what we call an extraneous solution. And so our one and only proper solution to this equation is x is equal to 2. We found it graphically, we verified it algebraically, verified it by plugging it back into the original equations, and so we can be reasonably confident that this is in fact our unique solution. So I hope this helps. I know graphing these kinds of things can be tricky. There's more than one way to go about it, but I like this method of graphing the square root of whatever function we might be dealing with, and then any kind of simpler transformations can be handled at the very end. So I hope this helps. If you guys have any questions, any comments, any suggestions for videos on similar topics, or even different examples on this topic, please leave a comment below. I would be happy to receive more suggestions for videos. But I hope this helps, and thanks for watching.